start, I wanted to make a few announcements and put them down there. So there's the final exam on Friday. Unfortunately, the registrar's office has put us at the very first final exam. So semester will officially end on Thursday and we'll have the final on Friday. It leaves very little time to review stuff. So I would urge you all to not wait until the last minute, but review material sooner rather than later. I'm around all week if any of you have questions about any of the material covered. Come by. If you need to come by at a time other than office hours, I can still be available. Okay, so I'll try to be somewhat flexible on that regard. I did mention that although Lab 3 is officially due this week, you can take a no penalty extension and turn it in next week. Okay, just to ease the burden, because I would normally have expected the final exam to be next week, which is really when most of the finals are, but unfortunately scheduled for Friday. Okay, so those are two things that are still due. Field trip is on Thursday. Okay, I presume that the Friday final would discourage you from coming. For those of you who have signed up, I am trying to make sure we will have enough cars to go. If you don't have a ride, I'm trying to arrange rides and whatnot. Okay, so we are close to the 20 limit that I had indicated to the people there. So they are expecting a group of around 20 and we are right around that limit. Okay, if any of you had not signed up but is interested, let me know, because I am going to probably have to make arrangements for a ride unless you have a car or a car. Okay, so I need to know in advance. If you just show up, we may not have enough cars to take everyone. Alright, so that's field trip. And then as far as lectures are concerned, we really have 2 classes, and then there is an extra class the university has scheduled as a snow day on Thursday. Okay, so I'm going to just do some sort of a wrap up on Thursday. We'll have today's lecture focus on distributed pervasive systems and green computing, and next class will be on middleware. Okay, so those will be the main topics. I may talk a little bit about security on Thursday and then do a wrap up. Okay, so let's start. So what I'm going to do today is start talking a little bit about distributed pervasive systems and sensors and sensor networks and things like that. That's the first part of the class. Second part of the class, I'm going to talk about green computing systems. Okay, they are not the same, but they are somewhat related, as we will see. So let's get started with what is pervasive computing. So if you remember the very first class, when I was talking about history of evolution of distributed systems, I said computing has become pervasive, which means that hardware has become very cheap. Okay, you can now put computing devices or sensors everywhere in the environment, and there are things that you don't even consider to be a computer that actually have a lot of computing in there, whether it's cars or buildings or sensors and so on. Okay? So what we are going to look at is from a distributed systems perspective, we'll look at what are some of the issues that arise in designing distributed pervasive systems. Okay, so in that context, I'm going to also talk about the rise of all sorts of smart devices that you are seeing today, smart cities and smart homes and buildings and so on. And I'll talk a little bit about some of those. So there are some pictures of these devices here. That's an in-car entertainment system. The cars have lots of computing systems and sensors built into them. There is a photograph of a washing machine. That's a smart washing machine that can be controlled remotely. Smart TVs and whatnot. Okay. So if you look at this trend, I think if you read articles on some of these trends, you'll see here the term Internet of Things or IoT. Okay, what that basically means is there are these devices that have computing and sensing embedded in them. They have networked capabilities, so these devices are networked. Okay, and many of these devices have the capability to be accessed remotely over the internet, and hence the name Internet of Things. The things here are the devices. Okay, and you make essentially a network of these devices, which gives you this term of Internet of Things. The more technical term that people have used are either sensor networks or network embedded systems. Okay, they roughly mean the same thing. The term Internet of Things is more popular in the popular press and whatnot, and if you look at more of the research literature, you will hear things like network embedded systems or sensor networks. And we'll look at some of this in more detail, but essentially the technology trend that is driving all of these, whether you call them Internet of Things or sensor networks, is the miniaturization of computing. Right? Essentially, we will see computing devices with very small form factors. Okay? They are much lower end than your typical desktops and servers and so on, but nevertheless, they are tiny computers in their own right, and because the form factors are very small, you can now put computing in lots of other devices, okay, that you would normally not expect to see computing devices. Okay, so that's really how some of these trends have come about. Okay, so I'm going to start with applications, and then we'll actually look at some specs of a platform so that you understand what miniaturization means. So here's an example of a smart home or a smart building. I'm going to come back to this at the end or the latter half of the class, and we'll look at smart buildings in a lot more detail. But here are some commercial products that you can actually buy today, okay, from a retailer. So there you can get light bulbs that have remote control capabilities. Okay, that's a Philips light bulb that just looks like a normal light bulb. You can turn it on and off using a switch, but it also has internet capability, which means you can also control it from a smartphone or a desktop browser or whatever. Okay, so that's an example of a smart light bulb. Okay, here is an example of a smart outlet. Okay, so what that does is basically you plug that into the wall, into a normal outlet, and then you'll see that that outlet itself has another outlet, so you can plug anything you want in it. But what that outlet has is also the capability to be remotely controlled, so you can turn things on and off using your phone or through a program or through a browser. Okay. You can see that there is a remote controlled garage door opener. Instead of using a typical remote device, you can use a phone and control it over the internet. There are smart thermostats. This one is called a Nest thermostat. It's built by Google, that allows you to control your air conditioning or heating in your home. But again, it has the capability to learn what the user wants and automatically program it, so you can control it with a phone. Okay. So these are all examples of commercial products that are already available today. Okay. And this trend is just continuing. So practically any device that you can see, there is a trend to put some computing and remote control capability or networking into that device. Okay, so this has led to this rise of all the smart devices and Internet of Things. Okay. This is another domain. Okay, the first one was smart home. Here is a different domain, which is health. Okay, this health and fitness is another big market where there are lots of these smart devices that you can buy off the shelf today. Okay. On the left, I have all these so-called fitness trackers that you can buy. Okay. What they do is they basically count your steps or count how long you have run. They can monitor your heart rate and whatnot. And they have some networking capabilities so that they can upload all of this data to a remote server, and then you can access that data to a phone or a browser and so on. So this allows you to track various fitness parameters if you're interested in it. Here is a smart scale, okay, so you can not only weigh it yourself, but keep a record of your weight over time, because it has Wi-Fi capabilities and it can upload that data. And you must have all heard of the Apple Watch and all these smart watches that are now beginning to appear on the market, which do similar things. Okay, so they have the ability, lots of sensors that allow you to track fitness and whatnot. Okay. So that's the second domain. So there are two domains, and there are many others. So these are just examples to give you some perspective of what miniaturization has been able to give us in terms of computing and communication and so on. Okay. So the typical architecture for many of these products, there are many such products, where typical architecture is there is some device that will have some computing, communication capabilities that get built in. Okay. and there will be different kinds of wireless networks that you could use to communicate. But often that device will be paired with some sort of a smartphone, okay, that allows you to access data from the device or control that device. And there is also some data that's stored on remote servers in the cloud. Okay, so there will be a cloud server that has the archive of the data. The phone can either be a relay to get the data from the device or send it to the phone, or it's just a device that allows you to view the data or control the device itself. Okay, so there is ability to access and upload data, there's ability to do remote low power communication, the ability to also provide analytics and feedback using the phone. So a lot of these products have the same sort of architecture. I showed you a smart bulb, I showed you all these fitness trackers, they all have the same ability, the sensing and communication and computing. Okay, then there is a phone that is either used as a platform to access that data or relay that data, and there is a cloud server which may archive it. Okay? So that's a typical architecture for an Internet of Things type product. Okay? The same thing is mentioned. So let me just pause here to see if there are any questions before I go into some examples of what kinds of specs you can see on these platforms and so on. Any questions? I presume you all at least heard of some of these things. It's not something that's you're hearing for the first time. Okay. So what I'm going to do next is to give you some flavor of the platforms that you can use to build products like this. There is a wide range of these platforms. I'm going to give you some point examples just to give you some flavor of what they look like. So by and large, you should think of them as highly resource constrained distributed systems. Okay. This is the reason we are even discussing this. Okay. So far we have assumed that all of our nodes in a distributed systems are typical computers. They are servers or workstations that are capable, they are communicating over some sort of a high-speed LAN or WAN links and so on. And we looked at several issues that arise in that context. Okay. This is the other end of the spectrum. Okay. Here devices are not standard computers or workstations or desktop, they're really small embedded microcontrollers or other kinds of platforms, much lower end capabilities, as we will see. Nevertheless, they are still a distributed system because they are nodes that communicate with one another over a network. They fit our definition of what a distributed system is. But the issues that you have to deal with in designing such systems are very different because of resource constraints. Okay? Some issues are no different, but many others will be very different. You can't run very high-end computations and things like that because the capabilities of these devices are very different. So here are some examples. Yes, so they may have wireless capabilities. The bandwidths you get using these radios will be in kilobits or tens of kilobits a second, not megabit or gigabit speeds. Okay, very low rate communication. Okay. The CPUs that you see on these devices likewise will be very low end CPUs, which may be 8-bit architectures with barely 4 kilobytes of RAM. Okay. As opposed to you're having 32 or 64-bit architectures and gigabytes of it. So orders of magnitude lower in some cases. Okay, you may have flash storage, and all of these devices will have some sort of sensors. But perhaps most importantly, these devices often tend to be battery powered or self-powered. Okay? That's a big difference from whatever we've been studying, where you assume that the machine is plugged into an outlet and it can just draw power from electricity from your electric grid. Here, often these devices, because if you're wearing a watch, it's not going to be plugged into anything. You would have charged it, it would have a battery, so it has to run off a battery. So a lot of issues are driven by battery lifetimes and so on. And we'll see there are some that don't even have a battery that harvest energy to power themselves. Okay. So I'll show now some examples of each of those things, which is computing, communication, storage, and so on. Okay, so here are some examples of CPUs that you would see on these devices. Okay, these are just specs that I pulled out, and there's a wide spectrum of these microcontrollers, which are essentially low-end CPUs that you can use, and depends on what kind of device you are trying to put together, and that's going to dictate the choice of what CPU you pick. Okay, so here is an example of an Atmel CPU, okay, AVR CPU. So it's 8-bit architecture. Okay. As I said, 4 kilobytes of RAM, there's 128 kilobytes of flash, okay, and it draws about 8 milliamps of power. Okay, very low end CPU. Okay, so think of writing a program, okay, that is going to fit in 4 kilobytes. Okay, that's the size of whatever your application you want to put on it has to actually fit into that RAM. Otherwise, you will not be able to get your program to run. Okay, so very different way of thinking about how to write distributed applications. So here is another one. Okay, this is a little more capable. This is a TI MSP 430 microprocessor. It has 16-bit architecture as opposed to 8-bit. It has 10 kilobytes of RAM. Okay, more than 4 kilobytes of RAM, 48 kilobytes of flash, draws 2 billion. Okay, so these are 2 example microcontrollers. You will see a broad spectrum with different levels of capabilities. Here are somewhat higher powered, but nevertheless low-end, low-power microprocessors. These are from the ARM family. If you've heard of ARM processors, okay, which are different from x86 processors. These are processors that you actually see on phones and tablets and so on. And then there are some products that you will see in Internet of Things that are going to be ARM-based. Okay? They are more like desktop class processors, but lower powered. Okay, so 32-bit processors, 1 megabyte of RAM, not gigabytes of RAM. You're still talking about lower end. You of course get more RAM depending on the processor, but this one actually has only 1 megabyte of RAM. That's an ARM7 processor. Okay. ARM9 is a more modern processor. So this one of these is the most highest, and 32-bit, 400 megahertz clock speed. Okay, it's beginning to look like desktop processor, 16 MB or greater RAM. Okay. So what this should tell you is, there's a picture of one of these MSP 430s there. I will not go into it. But what this should tell you is, depending on what kind of smart device you're trying to build, okay, you have to pick some processor family. Okay, but typically the processor family will be much lower end than what we are used to in our standard server-based distributed system. Okay. So how you program them is different. There are different languages or embedded tools that you need to use to program them and so on. Okay. When some very low-end ones won't even run an operating system. The entire program is the only thing that's going to run on it. Okay, the more capable ones will actually have an OS, and then the programs or applications run on top of the OS. Okay. So that was the CPU. Here are examples of some communication radios that you put. Often most of these devices will be networked, but they will have wireless capabilities rather than wired capabilities. And they will use radios that are different from what you may have encountered. Typically, when you say wireless, you think of Wi-Fi. Okay. Wi-Fi radios are much higher powered in that they consume a lot more energy than some of these radios. Okay. If you have a tiny device that's battery powered, if you put a high-end Wi-Fi radio, it will just run down the battery very quickly. Okay. So you need to also consider, just as you had higher end processors and low end processors, you see the same thing in the communication where you have higher powered radios and wireless radios and low power wireless radios. So here are some examples of lower powered radios. They often operate in either the 430 megahertz, 900 megahertz or 2.4 gigahertz band. They're all unlicensed bands, so you can use whatever protocol you want in them. Okay, so here are some examples. There's one called Zigbee, which is IEEE 802.15. Okay, it's a low-powered radio that uses 2.4 gigahertz band to communicate. And there are many such. Bluetooth is an example of a much lower powered radio than Wi-Fi. Bluetooth, I assume all of you know or heard of. Okay. There are many smart devices that now use something called Bluetooth LE, which is Bluetooth low energy. Okay, so that's an evolution of Bluetooth, which is designed for these smart devices so that they can actually run on low powered batteries and whatnot. Okay, so Bluetooth is a competing wireless protocol. There are many others. There's one called Z-Wave that is very popular in home automation. Okay. There's one called Threads, not Threads, Threads. Okay, so that's a wireless radio that Google is designing, okay, and the protocol stack. Google is designing that competes with Zigbee, for example. Okay, it's also meant for home automation. There are many others like that. Okay. So these radios Okay, they will have much shorter range because they have much lower power. They are not going to operate over long distances. Okay, the range is going to be some number of feet or tens of. You have higher power and higher range. Okay, if you put low power, you are going to compromise it by having somewhat of a lower range, unless you also drop the bandwidth. Okay. So there are trade-offs. Okay. So there is example radio that many researchers use, which is called a CC2420. Just as an example, there are some power statistics here. So it takes 9 milliamperes with tens of milliamperes to send and receive packet, which is much, much lower than what a typical Wi-Fi radio might need. Okay. So these platforms would also need to pick a wireless radio. It would need to pick some sort of a low-end processor, and you would need some sort of storage. Okay. Storage on these devices tend to be solid-state flash devices. Okay. You've probably seen these SS flash devices. Those are the same micro SD cards that you put in cameras and phones and so on. Okay. So those are all examples of what are called NAND flash based storage devices. It's called solid state storage. Same technology that is used in SSDs. If you use or have seen SSD disks, okay, they also use flash based storage. Now these devices, they look similar to a standard storage device, but internally they are very different from how you write to magnetic disks and so on. Okay, I briefly alluded to this when we were talking about RAID storage, if you remember, talking a little bit about SSDs. There are several examples. So one example, a difference between flash storage and typical magnetic storage is you cannot go and overwrite some data once you have written to a location on a storage device. Okay. You have to run what is called an erase cycle before you can overwrite. Okay. So once you write to a block, let's say write to a storage block, you can't just go and overwrite that block. Okay. You have to run an erase cycle and scrub the block before it becomes writable again. Okay. Unlike magnetic disks where you can go and write to any block any number of times. Okay. There's no concept of erase, you can simply overwrite it. Okay, there's a difference here. And because erase is slower than write, typically how you will put a file system on this device is going to be very different from how you write a file system or how you design your file system for traditional magnetic disk based storage. Okay. And there are many other differences. Okay. Some other differences include you have to run garbage collection because of the way the file system typically writes. You basically don't overwrite a block. You use log structured layouts or similar layouts that you just go and if you need to update a block, you just write it to a new location rather than running an erase cycle, which is going to be slow. Okay, that means you need to implement garbage collection on these storage devices. Okay. So some things get easier, but many other things get more complicated. Okay, these storage devices also tend to be much lower powered than magnetic disks because there are no moving parts. In magnetic disk, you have a platter that's going to keep spinning like a CD or a DVD. Here you don't have any such thing. Okay, you just can write to it as if you're writing to memory, except that it's non-volatile storage. Okay, that clear? Any questions on this? So last is battery power. Okay, so there's a picture of one of these nodes here. This is a somewhat old node at this point. It's called a Mica 2 board. But you will see the size of the entire device. Okay, there's a USB port, so you can actually plug it into a USB port of a desktop. But the entire CPU, storage network, all of that is on that form factor. Okay, it's sort of a small node. Okay, there are nodes that are even smaller than that. This is actually quite old at this point, but it just gives you some idea of what these computing platforms look like. Okay. Now the most important part, as I was mentioning here, is most of these will be deployed in an environment where you can't simply plug them into AC power or some power outlet. Okay, so they have to be powered using a source such as a battery. Okay. And this is where I think some interesting issues come up because batteries have limited lifetimes. Okay. You have to make energy efficiency of that platform becomes very important, both from a choice of what kind of hardware you pick, what CPU, what radio you pick, as well as how the software is actually designed. Okay. You have to design the software assuming that the node is not going to be up all the time. Okay. Fundamental difference. If you have a server, you assume that if the server is powered up, it's actually operating. Whether there's anything running or not, it's actually operating. Okay. If you operate these nodes in a similar fashion, it will run down the battery in a matter of hours. You can't go around changing battery every few hours. Okay. So what these nodes typically use is they use a power management technique called duty cycling. I don't know if any of you heard what duty cycling means. Duty cycling essentially says put the node to sleep for a certain period of time, okay, and it wakes up. Okay, it's duty cycle. It wakes up, it does some computation, communication, whatever needs to be done. It does that, and then it goes back to sleep for some more period. Okay. And you can define your duty cycling rate, which says for what fraction of time is the node up. If your duty cycling rate of 10%, then that says for 10% of the time in any given period, the node is up. For the rest of the time, it's actually sleeping. It cannot do anything. Okay? So now you have to design your distributed system or application, assuming that the node is going to be asleep for large portions of its lifetime. It simply doesn't have power to be up all the time. Okay? In many examples, that is actually going to be true. Okay? So you will use some sort of power management techniques. Duty cycling is one popular one, so that you conserve battery life as much as possible. Okay. The other interesting thing that many people have looked at is not use a battery at all. Okay. Instead, you are going to actually harvest energy from the environment. Okay. You can put a very tiny solar cell. You must have seen the solar cell calculators and solar cell watches that you used to buy off the market. You can put a very tiny solar cell that will power it, okay, whenever there is light around it. But there are more interesting ways to harvest energy that people have looked at. You can use vibration in the environment to harvest it. You can harvest energy using network wireless communication. Okay, all these wireless signals has a little bit of energy in them. You can harvest that energy from stray wireless signals and use that to power them. So if you do that, you will not need any power source at all. And you will not need a battery because it's self-powered. It's either using light, vibration from the environment, or some wireless RF energy from the environment. You can harvest that energy. Okay, you store it, you use it. Okay, and then you continue to, and then you go to sleep until you harvest some more energy. Okay. This will allow you to extend the lifetime to perpetual, to having a perpetual operation, but the amount of energy you can harvest is somewhat limited. Okay. Because you put a tiny solar panel, it's not going to give you a lot of power. It's going to give you a little power. So you have to still operate in a highly energy constrained regime. It's not like you're going to have a lot of energy suddenly to use. Okay. So you can use batteries, but then you have to use techniques that will extend the lifetime, or you can harvest energy. It doesn't use any batteries at all. But in either case, you are limited resources in terms of energy. And you, of course, the node itself is highly limited in terms of resources it has. So that's the platform itself. Okay, that's a tiny computer, as you can think of. It has a CPU, it has RAM, it has storage, it has network capabilities. Okay, and then you can put whatever sensors you need for your application that you're building. So you can just pick any subset of these or others, temperature sensors, humidity sensors, accelerometers, you can use GPS, you can have imaging sensors, which are actually cameras, light sensors, and acoustic sensors. So depending on what application you are actually building for your smart device, you will need some set of sensors. So those sensors will be the ones that will actually do the sensing. And you will use the node to acquire that data, do some local processing, and send that data out to some other servers. Okay. So those are the raw elements of how do you build some sort of a smart device. You will need a sensor platform, okay, which is like what I showed here, and then you will need some combination of sensors, and then you write your application that performs whatever tasks you need to perform. Okay. And that typically means you need to use some sort of embedded tools or embedded programming to program that node. Okay. You can't use, typically, you cannot use your standard Java languages because they will not even run on these low-end nodes in many cases. Okay? Any questions here? So I already mentioned self-harvesting sensors, which are using solar panels and vibration, airflow, wireless energy is an active area of research. A lot of research actually being done in this department of school. on that topic. How do you harvest energy from the environment so you never need to put a power source on your device. Okay. Very useful if you are having a watch. If it doesn't need to be charged every day, it's much more useful than if you actually have to go and plug it in every 24 hours. Okay. Just as an example of how self-harvesting sensors make life much easier when you try to build your application. So here are now the larger design issues. So whatever I was talking about was the design of a single node, okay, within your network. Okay, so you pick a node with some capabilities, and then typically your application may have more than one node. So here is an example that is shown. Okay, so you will see that these black boxes here are actually individual nodes of the kind I was talking about. There are sensors on them. Okay? And they can communicate with one another using whatever wireless radio you put on it. Okay? There will be gateways that will take that data, okay, and then that data will be relayed to some remote servers which are shown here. Okay? These could be servers in the cloud, or they could be some remote servers sitting somewhere on the internet. Okay, that's a remote server. And then you have clients which are actual users that are accessing them using your phone or your desktop or laptop or whatever other device you will need to use. Okay. So that's a typical end-to-end architecture, going from individual nodes to networks of these nodes, which is essentially a sensor network, to going to remote servers, okay, and the ability for users to either access data or control these devices somehow. And then depending on which part of the architecture look at, there will be many issues. Single node issues we already talked about. You have to decide what computing platform to use, what communication radio to use, how much storage to put on these devices, and so on. Okay. Then once you make a network of those devices, there are many other issues. Okay. So the duty cycling, the data aggregation and routing. Typically those devices are not going to have a long range so that they can directly communicate with a gateway or an access point. Okay. They may have to relay that data through other nodes because they have a limited range. Okay. So your nodes may not only have to do local sensing, they may also have to act as routers for data from other nodes so that all this data will flow over this sensor network to a remote gateway. Okay. And as you do that, you may aggregate data from nodes and send aggregated data to the gateway, or you may do other forms of in-network processing. Okay. That will reduce the communication, overall communication from the nodes all the way to the gateway. So these are all important design issues. Okay. What's the topology of your sensor network? Okay. What duty cycling rate are you going to pick? So let's say you pick a 10% duty cycling rate. Okay. That means 10% of the time a node comes up. Okay. When the node is up, it tries to communicate with another neighbor, and that neighbor is asleep because it's also a duty cycle. You cannot communicate with that node. Okay. So then you have to synchronize the nodes so that they all wake up, or at least your neighbors wake up at the same time. Okay. So then you'll have to ask, how do you go about synchronizing? We talked about clock synchronization and so on earlier. You'll have to use similar techniques here to synchronize nodes so that they are duty cycled in a synchronous way, that they can communicate with one another. Okay, then you have to think about what's the right way to route it, so that if you have to send the data to other intermediate nodes, you don't want to synchronize too many of them or have too many hops to the gateway, okay, which is only going to cause more challenges in getting the data to where it needs to go. Okay. So all of these are issues that arise in a typical sensor network design. Okay. I went through a whole bunch of them in 2 minutes, but each of them is actually quite a interesting topic in its own right. And there have been lots and lots of papers written on each of these bullets here. Okay. How to do localization, synchronization, duty cycling, aggregation, routing, and so on. So are all key issues when you go about designing a network. Next question.
Could interrupts be used as a way to synchronize?
Question is, can interrupts be used to synchronize devices? So what will typically happen is, these are wireless links. Okay, so essentially somehow, if this node needs to relay data to this gateway through this other node, as you've seen in this path, when this node wakes up, this other node has to be up, otherwise it cannot send it any data. Okay? So there has to, either you have to synchronize them such that they wake up at the same time, or the other way to do this is these nodes can be in low power listen mode, where you can actually send them some data and wake them up. You can also do that. They're similar to wake up on LAN technique. There are many different ways to do this. Yeah, all of them have been studied and there are many different techniques. So now how interrupts can be used, I'm not quite sure, because you can't send an interrupt to another node other than to send it a packet, which is essentially a way to wake it up. Okay. So, but those are all interesting issues. How are you going to ensure that you're synchronized in some way, or wake up nodes that need to communicate with one another? Okay. You never have to think about this when a client sends, in the client server world, and a client sends the data to a server, request to a server, you don't assume that the server is asleep. First I have to wake it up or I have to synchronize with the server. If you assume that the server is up, that's not the case here. If you communicate with another node, that node may not actually be up. So communication may not be even feasible sometimes. Okay. Yes?
Is there any estimates on the amount of traffic on which from the sensors, whether now or in the future, help match up?
You are asking what's the traffic demands, how much traffic is being sent. So question is how much traffic is typically generated by these sensors and what kinds of network bandwidths are you going to see. So to an extent the answer is going to depend on the application. Like what is the sensor network for? Okay. And you will see
just talking the whole internet, what fraction of internet traffic will be for?
oh what, okay, so you are asking different questions. Let me answer both questions. So you're asking what question of the traffic from these sensors fraction of the internet traffic. At the moment it is very low. Okay. The reason is internet traffic is dominated by video. Okay. Netflix itself takes a significant fraction of the total internet traffic, a single application. Okay. When there's video traffic that's hogging all of the bandwidth, all of this is noise at the moment. Okay. But as these devices grow, eventually they'll grow to dominate the number of nodes in the internet, and at that point they may become somewhat non-trivial amount of traffic. Okay, so that's the way to think about it. So it's not a whole lot right now. Okay, but it is in the future, you may have 100 times as many sensors as there are actual nodes on the internet. Just as today mobile devices now are exceeding wired hosts. Soon sensor devices are going to exceed anything that people carry around with them. At that point they may become non-trivial. At the moment it is not even going to appear, it's going to be the noise. Okay. Now I'll also answer the other question that I thought you asked, which is what kind of bandwidth do these sensors generate? Okay. That depends on the application. Okay. If your temperature sensor is going to generate an integer value, which is the temperature it's sensing, that's not a whole lot of data. Temperature is not going to change very frequently either. Okay. It's going to change very slowly. So the amount of data that you may need to send is very low. Okay. On the other hand, you may have an image sensor network, which is essentially a network of cameras that's trying to perform some task. Okay, whatever that task may be image recognition and so on. So in this case, the data that you're acquiring is an image, or it could be a low bit rate video stream, okay, that you are generating, and they are sending that over the network. In that case, your network communication need may be orders of magnitude more than what a temperature sensor will generate. Okay. So you will get a different design points based on what is the application, what's the sensor, and what is the rate at which you are sampling the data and how much data is it generating. Okay, but nevertheless, in the aggregate, still as I was mentioning, sensor networks don't generate a whole lot of traffic in the internet today. Okay? The internet part only starts the gateway onwards. Okay? These are private networks. Okay? They are not typically, today they are not networks. So you basically send the data to the gateway, and then the gateway can talk IP. Okay? Or TCP IP. So gateway on you are talking TCP IP, but not all the way to the sensor. Okay? That is also changing. Okay? There are all sorts of activities to put IP level networks on the sensor devices themselves. Okay? So IPv6, there are variants of IPv6 that are pushed all the way to these devices. Okay? So in that case, each device is going to actually have a real IPv6 address, and you can directly address it as if you are addressing any other node. Okay, so that doesn't actually happen. It's something that people are looking at, and there are prototypes built and so on. By and large, today's architecture says These are some low-end wireless radios, okay, that basically don't talk IP stacks. Okay, they basically use some proprietary protocol. They send data to a gateway which is IP enabled. This is an IP-based gateway. From this point on, so that's the way to think about it. So the last part of the architecture is the server side. Okay, once the data flows out of the gateway to the server, you can do a variety of things. You can do analytics, you can do processing, you can do machine learning and try to derive some interesting insights as to whatever that data is telling you. So all of that typically runs in the back end because those devices don't tend to have the resources to run these computational tasks. They can perform some limited local processing. Most of the heavy duty processing has to happen on remote servers. Okay, so you can do all of those on remote servers and then perform actuation or make recommendations and so on. And vice versa, the user wants to control those devices. You will either use a browser or a phone to send a command. Command will typically go to the cloud server. Cloud server will send it off to the gateway, where the gateway will probably forward it to the device. Or if these devices talk IPv6, you may not need the gateway. You may actually be able to send it directly from the cloud server. Okay? Questions?
Are there any protocols about how the gateway talks to the devices? Are there any standards that are developed?
Question: are there protocols or standards of how gateway talks to? So there are many protocols and many standards, none of which have actually become de facto. There are research papers that are written on how to do this in network aggregation, how the gateway will talk to this, how routing happens. All of this was studied extensively or is still being studied in some cases in the research. And there are products that will do that. If you have a Zigbee network, for example, Zigbee will define what's the role of a gateway, how addressing in Zigbee works, how routing has to be performed and relaying has to be done. So that's 802.15, which is an IEEE standard, just as Wi-Fi is 802.12. So there are standards as well. Okay, but there is no one protocol that has become dominant. There are as many protocols and new ones are popping up every day. Okay. So that's all I have to say about sensor networks. So the rest of whatever time is left, we will talk about green computing, okay, which is slightly different topic, but the common theme between the two is these are all energy oriented topics. Just as energy and low power is very important in the context of sensor networks, we'll see that green computing is all about being green and energy efficient. So when people talk about this field of green computing, they actually mean one of two very different things. Okay, one is what is called greening of computing. Okay? The other one is what is called computing for greening. Okay? They are actually two different things. Greening of computing, simply say, is the problem of how do you take your standard servers and desktops and so on and make them more energy efficient and make them consume less power. Okay? That is what is referred to as greening of computing. So you take standard computing devices, desktop, laptop, servers, and you make them more energy efficient. This is called greening of computing. Okay? This is an old area of research. This is standard computer science research when you do operating systems work, for example, okay, or networking for that matter. And this area has been around for a long time. There's been a lot of work done in that context. I'm going to speak about a very specific version of that, which is making data centers more energy efficient. You heard about data centers last time in the guest lecture. We'll talk very briefly about making data centers more energy efficient. This is especially interesting in the context of this field trip that some of you are going to go on Thursday. Because the data center we are going to go to is a green data center. It's one of the more energy efficient data centers that has been built. When you go there, you will see what techniques they use to make their systems greener. I'll talk more generally about them here. And so that's one part of green computing. The other part of green computing is very different, which is how do you use computing techniques to make physical systems more energy efficient, whatever that system may be. It could be make a car more energy efficient, or it could be make a building more energy efficient. You can make the highways smarter and more energy efficient and so on. So in that context, I'm going to do a case study of making buildings more energy efficient. Okay, here we are using computing techniques We are going to use sensing, we are going to use communication, we are going to use computing that is embedded into that physical infrastructure. And we are going to use that computing infrastructure to actually reduce the energy usage of that entity, whatever that entity is. Okay, in this case, we'll do a case study of building. Okay. So two different topics. When you hear the term green computing, okay, typically you may think the first one, because that is what has been studied for a long time. How do you take computing equipment or communication equipment and make it more energy efficient? This is very different. This is an emerging area that has actually arisen in the past few years, and I'll talk a little bit about both. Okay. So some history here, I think I mentioned some of this already. Okay, making computing devices more energy efficient is a long studied problem. Okay. Especially in the context of mobile devices, this has been studied for decades. Okay, because it's simply problem of you have a laptop is battery powered, you want to extend the battery life. What OS techniques can you use or hardware level techniques can you use to extend the battery life of your laptop? Okay. This could be you turn off some parts of the laptop which are not in use. If the disk is not being used, you can spin down the disk. Or if the screen which can consume significant amount of energy, if there's no activity, you can turn the screen off. There are many OS level power management techniques that have been studied for a long time, okay, in the context of mobile devices. More recently, the emphasis has shifted from mobile devices to servers. Okay, so how do you make servers more energy efficient? And the reason this has become important has been due to the growth of data centers. Okay, so with all of these internet services that you see today, most of them will be running on some data center or the other. Okay? Data centers are really large clusters of servers. When you have lots of servers, they will eventually consume a lot of energy. And so making them energy efficient is more cost effective. It reduces your operational cost, as we will see in just a moment. So more recent research in this area has focused on data center energy management or power management. How do you make very large distributed systems, which are essentially data centers or servers, clusters, more energy efficient? I'm going to show you calculation just to give you some sense of why this is important. So let's take a typical large data center. Okay. Let's by large I'm saying 100,000 servers. Okay. Let's say I have 4 cores, so that has 400,000, or if it's 16 cores, you'll have more than 1 million cores in that data center. So a typical server may consume up to 500 watts. Okay. That's a number I pulled out. It can vary. It could be anywhere from 200 to 500 watts, but just for this back of envelope calculation, let's say one server consumes 500 watts. You have 100,000 of these servers in your data centers. Okay? So the electricity cost, simply the electricity cost of just keeping the server on is going to be the watts that you consume, okay, times the hours that it runs, okay, and times the cost of electricity. Okay? So you take how many watts does it consume, how long is the server running, what does that's the amount of electricity it's consumed, and then you multiply it by the cost of electricity. Okay. So if you have a 500 watt server, let's say you take 10 cents an hour electricity cost, okay, this is a typical number, then the typical server is going to cost you $50 in electricity bill. Okay, just to keep it on all the time is going to be about $50. Now you have 100,000 of those servers. Okay. So if you keep them all on for the whole month, your electricity bill has gone to $5 million. Okay, that's your electricity bill for one data center. Okay. And we haven't even come to cooling these servers. But typically, that's not all the electricity your data center is going to consume. All of these servers are going to generate a lot of heat when you put them on. And when you have so many of them, they produce a significant amount of heat. So you have to invest a lot in air conditioning or cooling the data center. And typically, what you will see is for every watt of electricity a server is going to consume, you may need up to another watt to consume in your air conditioning or whatever the cooling infrastructure. Okay. So what that says is typically if you actually have a modern but not the most efficient data center, your electricity bill is going to be twice of this, because for every watt that the server has generated, consumed, you need 1 watt of cooling. Okay, so 1 watt of server power needs 1 watt to cool that. Okay, so that you doubled your total usage, so now your bill is actually doubled. So if you actually have a data center that's consuming electricity or generating electricity bill of millions of dollars a month, okay, you will be highly motivated to design energy efficient techniques to cut your bill down. You cut it by 10%, you already saved $500,000 or $1 million a month. Okay, that's not small amounts of money. So this should give you some example idea. This example should give you some idea why this topic suddenly became very important, at least to industry. Okay, because they are going around building lots of these data centers. Like Facebook and Google and Apple, they build much larger data centers than these, and they consume a lot of electricity. You have to pay very large bills, and that's every month. They are paying that much money to your electricity company. So energy efficiency of data centers became very important, and there's a lot of research that was done into how you can reduce the energy footprint of your data center, how can you reduce carbon footprint of your data center, and so on. Okay. And there are many techniques that we will see. Okay, I'm going to introduce one term here just so that you know. I don't know if this was introduced in the guest lecture last time. The term is called PUE, Power Usage Efficiency. I don't know if any of you have heard of this term. Okay, so this basically is a term that measures how energy efficient your data center is. Okay. And basically the way you compute PUE is typically the ratio of the total server power over the total power needed by your data center. The total power is just essentially this server plus cooling power. So it's the other way around. So you take the total electricity bill or total energy consumed by an entire facility, which is server plus cooling, and you divide it by the total server power. That gives you this term, what is called power usage efficient. And essentially, basically, the lower that number, that means the lower overhead you have beyond whatever your servers are consuming. Okay? The most modern data centers now are down to 1.1 or below. Okay? The standard number is PUE, is typical data center is 2. Okay? Because it's for every 1 watt of server, you need another watt of cooling. So basically, you will have 1 plus 1 over 1, which is you will get a PUE of 2. Okay? So that essentially says for every watt of server power, I have added another watt, so my cost is double. Okay, PUE of 1.2 here, which is some reasonably recent Google data centers, is at 20% overhead. For every 1 watt of server power, 0.2 watts of cooling power is needed. Okay, so I reduced my cooling infrastructure has become more energy efficient. Now you are down to 1.1 or 1.05, and the way you go about doing it is you don't actually use real air conditioners. You can simply take outside air if you are building your data center in cool climates. Okay. If you are in a very hot room, okay, all you need is a big exhaust that will just take all the hot air and just exhaust it and just bring cooler air from outside. That will cool your servers down without having to use a real air conditioner. Okay. Some data centers built by Facebook actually do that. This is called direct air cooling. Okay, direct air cooling is equivalent of open your windows in your bedroom. Okay, don't use a fan or an air conditioner. Just let the outside cool air come in and cool your room down. Okay, this is a similar equivalent in data centers where that's the only way you are going to reduce your cooling power needs, okay, by not using expensive chillers. Once you turn on chillers, your power needs are going to go up. They will basically be in the range of PUEs too. Okay, but if you don't use them or use them very infrequently, you can run your data center at much better efficiency. That's just the cooling part. Okay, there's a lot of work also done on the server part itself, because the servers themselves consume quite a bit of energy. You need even more energy to cool them. So, yes.
Okay, so what's the current technology you use in Google into cut down the cooling energy.
Okay, what's the current thing that is used by Google? So most of them will use what is called some form of direct air cooling or evaporative cooling, which essentially says you shouldn't use chillers. You're either going to have some water flowing through that, and the water is going to take the heat, and you will send the water to a cooling tower where you will just expose it to cold air, and then the heat will just dissipate. Okay, and then you'll circulate the cold water back. Or you're simply going to take, if you, let's say in the winter here, where the outside air is very cold, all you need is, if there's hot air inside, you just throw that hot air out and exhaust it out and draw cold, cooler air in. Okay, so there you don't need a real air conditioner to cool anything. Okay, so you're using much cheaper forms of cooling to do this kind of sort of cooling of data center. So most of the modern ones are going to use similar things. When we go on the field trip, you will see that the data center that's in Holyoke uses evaporative cooling. Okay, it basically has backup chillers. So if you have very hot summer days where outside air becomes very hot, you can't use it to cool anything inside, you turn it on as a backup, your air conditioning or chillers. But otherwise, most of the time, you're simply going to use other techniques to cool your data center. So that is what most of these modern data centers, Apple, Google, Facebook, they all use this kind of techniques. Okay. So as I said, the way you make the data centers greener are, you can cut cooling costs. That's what I was talking about on the previous slide. You can actually also reduce the cost of running your servers by making your servers more energy efficient. Okay, the OS can employ power management techniques, which says the server is idle. Okay, put it to sleep. Why is it running if it's idle? You can make it up on the fly. You can use virtualization and boot it up in matters of seconds and not have to wait 10 minutes for your server to boot up. Okay. So you can basically turn off idling servers. It's the single most effective use. Seems very silly, but the very most effective power management technique is turn off idling servers. Okay. The reason this actually gives you a lot of benefits is your data centers are heavily over provisioned. They are always built for the peak load. Okay. Peak load may be several times higher than the average load. So whenever your data center is running on an average load, the utilization of the data center may be 20% or 30%. It's very low, okay, because the peak load is very high. So if you're only running your entire infrastructure as 20%, a lot of servers are going to be idling or be running very low load. So you can turn them off and save energy. Okay, so there are lots of advanced power management techniques that say, how do you figure out what servers are idle, how do you turn them off, how do you turn them back on when the load peaks, and so on and so forth. Okay, so that's another active area of research. Okay, so I already mentioned all of this, intelligent power management, turn off servers where you're not used. Virtualization is another useful technique, because if you virtualize your application, you can simply move the virtual machine from one server to another. Okay, so if you have two servers, each of them are only at 50% utilization, you can, and if they are both running their application inside virtual machine, you can simply move that virtual machine from the first server to the second. The second server now runs two virtual machines. First server is idle, you can shut it off. Okay, the utilization of the second server has gone up, which is good because you are using its resources. Because if it's on and consuming power and you're not using resources, that's wasteful. Okay. So virtualization is actually a very useful technique for used in advanced power management in data centers. Okay, and then you can also, as I said, do things like just turn off servers when they're not in use. There are other things that are being used that are more on the hardware side. Okay. One thing that many efficient data centers do is they actually run their servers using DC power, not AC power. The reason that is useful is because your power supply is going to lose some efficiency when it converts from AC to DC. Okay, if you just feed in, most of these things will actually have an AC to DC converter. Your laptop, this power brick here is essentially going to convert your DC power, AC power to DC power. Okay, and it is going to have some inefficiency. It's not going to be 100%. Whatever it's consuming, there will be some loss. Okay. To eliminate that loss, if you directly feed DC power to your servers, okay, to get rid of that power supply that's inside that's doing the conversion, you are going to be more effective. Okay. So there are many energy efficient servers that just run on DC, not on AC. Okay. There are many such techniques that data centers will use to cut their cost. Cooling costs, as I mentioned, there are many things that better air conditioning, there's a lot of area there, but newer cooling, which is what I was talking about, Facebook and YouTube, they use is direct air cooling. Okay? And there are many experiments that have been done to show that because servers are built or engineered in a rugged way. Okay? They can actually withstand much higher temperatures than you normally would believe before the server starts malfunctioning. So here's an example. You can see that. That's an example experiment that was done by some researchers who essentially put some servers in a tent. Okay? And the tent was not even fully covered, so it was essentially just cooled from outside. It was exposed to the elements and it ran, and none of the servers actually failed even after 6 months of basically abusing the servers in this fashion. Okay? Not nicely designed closets or anything like that. Okay? Modern servers can run at 120 Fahrenheit, okay, without malfunction. Okay, think about that, 120 Fahrenheit. More, when you actually walk into a data center, they run their servers at 70 Fahrenheit. Okay, they are massively overcooling the server because the servers can withstand much higher temperatures. They are built to last even in much higher temperatures. So if you just use outside air, it may be good enough because all you need is temperature of 80 to 90, okay, not 60 inside your machine room to cool those servers. Because those are all ideas that have been used to cut your electricity bills. Okay, so I'm going to stop with data centers and move on. So that was all computing of greening of computing. I'm going to talk about computing for greening. The example here is going to be a smart building as a distributed system. Okay. So this is going to take some of the ideas from the first part of the lecture, which is all sensor networks, and show you how sensor networks can be used in a physical infrastructure to make them more energy efficient. Okay. So the way we look at now how to think about a building is it's not a building, it's actually we have to think of it as a distributed system. Why is that? Because we'll assume that it's an example of a distributed pervasive system where there are sensors embedded in the environment. Okay. These sensors could be as simple as if you look at this room, you'll see that in the corner over there, there is a motion sensor. Okay. That motion sensor is whenever it doesn't sense any motion in the room, if the lights are on, it will turn the lights off. That's an example of a closed loop control where you have sensing which is used to perform actuation. And it is put there to conserve energy because people may forget to turn the lights off. Okay, so the sensor is doing your job for you. If it doesn't see any sign of motion in the room, it will assume that the room is unoccupied and turn the light on. Okay. Same thing can be done. So lights are one example. Another example is using sensors to control heating and cooling. Okay. That's another big consumption of energy. Okay. Typically, heating and cooling bills are 50% of the total energy bills of a building. Okay. Same as for your house. Okay. If you actually pay your utility bills, you will see that 50% of that utility bill is actually going either in cooling or heating your house. Lighting is typically 20%. Okay. The remainder are other appliances and electronics and things like that. So if you could simply make one big improvement, it would be cut down your heating and cooling costs. That will give you the biggest savings, the biggest bang for your buck. Okay. So there's been a lot of work in smart buildings which is using sensing to figure out where are the people in a building. You take an office building of this sort. Okay. The standard way to cool it is somebody in the physical plant or facilities will make a schedule saying start cooling or heating the building at 8 AM because that's when people come. Okay. The entire building will be start cooling or heating at 8 AM. And then they will say at 6 PM most of the people are gone, so stop or reduce the amount of heating. So that's what is called a static schedule. Okay. But if you actually look at the building, it's not like every floor and every room is suddenly occupied at 8 AM and everybody is gone at 6 PM. Okay. The occupancy patterns will depend on what room and what building, what part of the building it is. The main office is staffed from, let's say, 8 to 5. Okay. Graduate students don't come in at 8 AM. They come in much later and they also stay much later. Okay. But the building manager is not looking at all that. He may be staying till 10 PM. They will stop cooling the building at 6 PM. Okay, if you start feeling hot or cold in the evening, that's not their problem. So what this is also telling you is the way you use air conditioning or cooling is not very efficient. It is done in some static way. It's not based on when people come in, when they leave, and so on. A more effective way of doing the smart buildings, if you have sensing, that is sensing when people are actually in rooms or labs or conference rooms, classrooms, and so on. And based on that, only that room is cooled whenever it's occupied. That's a much more effective way of using energy. Okay, you don't waste energy when nobody is there. Neither do you actually not properly heat or cool and cause discomfort. Okay? You will see that there are many labs where people have brought in space heaters because in the evening it starts feeling cold because they just turned down the heating at 6 p.m. thinking there's nobody in the building. That's not how many of the research labs will work because students will stay late, for example. And that's not very effective. So just reduce your effectiveness of it. So basically this entire area you can think of as you need to use sensing to do monitoring. You use sensing to monitor who is in the building, how much energy is it consuming, and so on. You use the sensing data to do what is called analytics and prediction. This is where you may use models, you may use things like data mining or machine learning techniques to understand what is this data telling you. Okay? What does it tell me about when the first floor is occupied, or so the second floor is occupied, or the third floor is occupied, as an example. And then you use these models to drive control. Okay? Control is where you actually control the lighting or the heating and cooling or any other aspect of your smart building. Okay? So you have this loop, which is also referred to as the sense, analyze, respond loop. So you are sensing, that driving the analysis, that driving the response, okay, which is typically controls or recommendation. Okay. A very standard technique to build is essentially a smart environment, okay, sense, analyze, response. So all of that is simply saying you're going to start from the sensing, then do analysis, and then do control. Okay, so I'm going to show you some things that you can use to do monitoring. Okay? So monitoring can be done at different levels. Okay, here are some products you can buy that do what is called outlet level monitoring. Okay? That's a device you can actually buy in a hardware store. Okay? It costs about $20. It is, you will see that it has an outlet and it has a small LCD screen there. Okay? The idea is you plug that into any outlet, and whenever you plug any device into this outlet, that display is going to show you how much energy is being consumed by the device. Okay? So, and there are variants of this where there will be a wireless radio so that this data is also being sent off somewhere. This is simply showing on an LCD display so you can plug it to whatever you want, your laptop, your television system, and see how much does it consume. This is one way of doing very local monitoring. Okay? You're just monitoring a single outlet. Here is another level of monitoring, which is you're monitoring the circuit breaker panel. You probably know what a circuit breaker is. That's where essentially the fuses for your home. So you can instrument, these are all wires, they look like a jumble of wires, but essentially what has happened in this circuit breaker panel is you put a sensor on each of the circuit breakers. So you can figure out if you have a circuit breaker for your fridge or your microwave or your air conditioner or your furnace. You can now monitor each of those circuit breakers. So you are no longer monitoring outlets, okay? You are monitoring circuits. Okay? And then you know what is being consumed. So if you now take all of those circuits and add them up, then they will tell you what the entire home or a building is going to consume. Okay? But you are doing a little more fine-grained monitoring than just the circuit breaker. And there are products that will do that and also show you on a display how much of these things are being consumed and sold. I'll show you an example in just a bit. So you can get that data and then start analyzing it. You can use, as I said, all of that sensing data, whether it's usage-based data or occupancy data. You can analyze it using models and learning techniques to understand what kinds of usages you see and so on. Okay, I'm going to show one quick example of monitoring as you can get it out. So here is a monitor that is actually showing you data of electricity usage of a home. Okay, so that's the usage over a 2-day period. There's live data being shown here. And the way it's being computed is all the circuit breakers are actually instrumented. So you will see there's a washing machine, and there is a dining room, and there's an air conditioner, and there's a furnace. So all of those have individual sensors on them, and if you pick them, you'll see there are green lines that tell you what's the usage of each circuit. And that's the total usage that you have seen over some period of time. And it's recording all of that data to show you how much data is being consumed and so on. So this is just an example of a monitoring tool that is monitoring the usage of a building, in that case it was a home. Okay. Once you get that data, and you can see it's accessible on the internet, so that sensor is actually networked and you can access it from a browser. You can also feed it to these programs that can figure out, do you have an inefficient furnace? Are you wasting energy in your house? Is your building's schedule, AC schedule aligned with occupancy pattern, which means the AC only runs when people are there. It neither wastes energy nor does it cause discomfort. Okay, what kind of peak load is your building going to generate? Okay? How does that impact whatever circuits your provision and so on. Because there are many things you can look at and try to reduce waste. Common example is to use this data to figure out where is wastage in the house, energy usage, and try to reduce that waste somehow, which will make your, in this case, the building more energy efficient. And that's what we mean by using computing for greening a building. Okay? You use sensing, you use standard modeling techniques and learning-based techniques to essentially get some insight as to where there might be waste, where are there opportunities to conserve energy. And then you all use that to optimize your energy usage. Is that clear? Any questions here? Kind of done here. The last slide here is on use of renewable energy, which is another important topics in the context of smart buildings. Okay, so here are some pictures of deployments we had done some time back. This was a wind turbine we had put on the roof of this building. It's no longer there, we moved it to offsite. These are some solar panels that we use to collect data of how much solar energy you can generate. Okay. The interesting thing here are two things. One is any of these renewable sources are what are called intermittent. They are not always going to generate energy for. Okay. Solar energy depends on weather condition and time of day. Nighttime there's no solar energy. Even during a day, if it's a cloudy day like today, it's going to generate far less energy than it's a sunny day. Okay? In winter, you generate less solar energy than summers. The summer days are longer, the sun is bright. Same with wind energy. Okay? If it's a windy day, you're going to generate more wind energy than if it's not windy. Okay? So they are intermittent in nature. And the important question there is, if you have these intermittent sources, how can you make effective use of locally generated energy? Yeah, and you use it when the energy is being generated. Okay. Simple example is there's a lot of solar energy that you may generate during the day, but during the day you may be in the office. Okay, but when you come home in the evening, okay, the sun has set, so there's no solar. So you are generating energy at the wrong time. How can you make use of energy when you need it? So you can't say I'm going to work in the night and stay in the day at home and use all the energy. That doesn't work, right? Instead, what you want is to use what are called energy storage devices. What would be nice is if you generate this solar energy, you put it into an energy storage device, okay, so that it's stored there. When you come in the evening, although you're not generating any energy, you can draw from the energy store. Okay? Car batteries are an example of how people actually use energy storage devices. You pick a big car battery in your house, connect it to your solar panel, it will charge the battery during the day when you're not at home. You come home in the evening, your panels don't generate anything, but all the energy is stored in the battery. Okay. Car batteries are actually a very bad example because they're not energy efficient. They lose a lot of what is stored in them, but that's an example of how you can use some of this renewable energy, store them, and then use them more effectively. So these are just examples of how can you make use of intermittent sources in a more effective way in smart buildings and so on. So again, all ongoing topics of interest to both researchers and industry and so on. There's a lot of work that is going on all of these topics that I have just been mentioning. So we are kind of running out of time. So we are going to stop here, and then there's one more slide, which is the people part. So so I talked about smart buildings and whatnot, but all of these patterns that you see, you can expose it to users using smartphones or web browsers. I already showed you this picture using that live data that was coming from a building. You can see the similar picture using a smartphone. You can control devices using your smartphone and so on. So that is where users also have to play a role. If you don't care about saving energy, nothing will matter. Okay, so making users more conscious of their energy usage and motivating them to save energy is another important problem. Okay? It's not easy to convince somebody to do something different. Because if in the end it's only going to save $1 of your electricity bill for a month, you may not care. It is too much work to save $1. Okay? Because not like your bill is going to reduce by 80% because you started turning off your lights in the house or something like that. Because you will only make small incremental improvement. So providing feedback and incentivizing users to do the right thing is another area of research. Okay? Because monetary incentives may not be sufficient when energy prices are cheap. Okay, electricity bills are not that high. How do you convince somebody to save? Worse, if you rent a house where utilities are included in your rental bill, okay, you have no incentive whatsoever to save any energy because you have already paid for it as part of your rent. Why would you ever turn down your heating when you leave your house if it's not going to make any difference to what you pay every month? So there are problems in terms of incentivizing users to do the right thing in such circumstances. Also important area people are looking into. Okay. So with that, I'm going to stop here today. Okay. We are done with distributed pervasive system. One last topic that remains is distributed middleware, which we will talk about on Wednesday. And for those of you who came late, we have a snow day on Thursday that's been announced. So I'm going to take advantage of that and have a short class on Thursday just to wrap up the course and go over some final topics. Okay. So let's stop today. We'll continue Wednesday.